I'll try to get it back to you this week. I don't know why that says recall. Never seen this before. I think I was recycling an old slide there. So last class we looked at stress around a wellbore, specifically a vertical wellbore. And it turns out we can apply all those same concepts to arbitrarily deviated wellbores, including horizontal wells, by just a rotation, just a coordinate transformation. And so this is very similar to what we did when we looked at stress resolution on faults. Now you might have wondered, if you're really good at geometry, you might have wondered when we did the stress resolution on faults, if you recall, we have the principal stresses essentially arbitrarily oriented. They're oriented however they are due to the nature of the tectonic stresses. And we would rotate them into this geographic frame. And then from that geographic frame onto a fault. And if you're good at geometry, you might have been able to say, well, if I know the principal stresses with respect to the fault, I can just work out the geometry right on the fault and don't need to go into this intermediate frame, right? Well, the reason I taught it that way there is because you do need to do it. I mean, you're going to have to learn it eventually anyway, right? Because you do have to use that concept when you're dealing with wells. So the idea here is that we're going to go from the principal stresses, however they're oriented due to the nature of the tectonic motion, into this geographic frame. And from the geographic frame, we're going to go into the wellbore, okay? And so again, the first part of that, the rotation from the principal stress directions into the geographic frame, you already have, right? That's the same code you wrote when we did stress resolution on faults, and you've tested it, and you know it works, and you all did very well on your exam, so you don't have to rewrite that part. So now we just have to go from the geographic frame into the wellbore, okay? And so just to clarify some things here. So our geographic frame was like north. I guess it's already drawn on this figure here. I'll draw it a little better. North, east, and down. Okay. So we have two rotations to get into the wellbore. One of them is a rotation that is the deviation angle, right? So it's an angle between. So if you draw a line straight down the center of the wellbore, the deviation angle, phi, is the angle between down and that line through the center of the wellbore. So, and this also works for horizontal wells. So if you have a horizontal well, what's phi? 90, right? So it all works. Phi is 90 for a horizontal well. Right? So then, I think that's pretty easy to visualize. Is everybody okay with that? What phi is? Okay. The one that's a little more difficult is delta. And what delta is, it's the angle of the azimuth of the toe of the well. It's the angle between that and north, right? So if we take the toe of the well down here, everybody know that terminology? Toe and heel, toe, right? I mean, so like, particularly when you have a horizontal well, it kind of looks like that, right, if drilled from the surface. So this is the toe, this is the heel, because it kind of looks like a foot, right? Of course, in just a deviated well, you don't really have a heel, but nevertheless, so from the toe of the well, if we were to project that back to the surface, like that, and then draw a line from the origin out, then delta is the angle between that and north. Right? Everybody okay with that? So to develop our rotations, we're just going to do them in isolation one at a time. We'll start with delta, right? So delta is a rotation about z, right? So rotation about z, remember right-hand rule, put your thumb in the down direction and curl your fingers. It's a rotation about z in the plane of north and east. And yeah, so if I draw north and east, and then draw another coordinate system, which I'll just call x prime, y prime, and then and the x prime defines the azimuth of the toe of the well, right? So in this particular case, the well would be drilled in that direction, in the direction of x prime. Then this angle is delta. And just like we have before, we can write down some rotation matrices. So if we want to write x prime, what is x prime in terms of north and east, then it's cosine delta north plus sine delta east. Y prime is minus sine delta north plus cosine delta east, and z prime is equal to down. All right? So then, if we have a Wellbore, it's originally sort of surrounding down, and then we have an arbitrarily oriented Wellbore that's oriented around a center line, what we'll call ZB, for Z around the Wellbore. Then this angle here and it's actually, let me draw it the right way. This angle here is delta, is phi, okay? And so then we need to draw the other axes. In this case, it's like xb and yb. And in this case, this rotation phi is about the y-axis, so yb is going to share an axis with y prime. So then if we write down the rotation matrices between this xb and the xb frame and the primed frame, then we have actually, before I do that, I meant to write, let's write, just write this in matrix form real quick. So x prime, y prime, z prime is equal to cosine delta sine delta 0 minus sine delta cosine delta 0, 0, 0, 1. That multiplies north, east, and down. Okay. All right. So back to down here, we have that xb is equal to cosine phi x prime minus sine phi z prime, yb is equal to y prime, and zb is equal to sine phi x prime plus cosine phi z prime. So that guy in matrix form is xb yb zb times cosine 0. Okay. So in both cases, I just used the shorthand. C stands for cosine, S stands for sine. So I have a way to go from the primed axis to northeast and down, and I have a way to go from the Wellbore axes to the primed axes. Then you should be able to see that I can just take that, if I can take the primed axes and replace this vector here with what's on the right side of that equal sign, then I have a rotation matrix times a rotation matrix that takes me from the borehole axis back to northeast and down. Okay? So if I do that, and what this guy multiplies out to, we're going to call RB, and it is that guy. And you can verify that for yourself. You can multiply matrices. So there it is. So if you're given the stress in geographic coordinates, and we know how matrices transform, right? Now we have a transformation matrix to take us from the geographic coordinates to the Wellbore. Or take it one step further, if you're given the stress tensor in the principal stress frame, and you have the rotation matrix to the geographic frame, then using this, basically we just replaced SG with RG transpose SRG, put that in there, and you have this equation here that'll take you from the principal stress frame to the borehole. Okay, so now remember our principal stresses are in Cartesian coordinates, x, y, z. And when we were working the Kirsch equations, develop those solutions, it's easier to work in polar coordinates. And so the transformation